Full disclosure, recording has started. Just want to make sure I get that out there so no one can accuse me of lucky it's not a video. All right, today, page 216. In the middle of the page is a little section that says practice problems. This is number 18 from the practice problem section. It is similar to the problem that we did yesterday in class, but there is one difference, and we'll talk about that difference in just a second. So it says, a stationary billiard ball, mass 0.17 kilograms, is struck by an identical ball moving at 4 meters per second. After the collision, the second ball moves off at 60 degrees to the left of its original direction. The stationary ball moves off at 30 degrees to the right of the moving ball's original direction. What is the velocity of each ball after the collision? So, two things we're looking for here, right? We're looking for V final of ball 1, and then we're also looking for V final of ball 2. Things we know. So we know the mass of each ball, right? It told us that the mass of this ball was 0.17 kilograms, and then it told us that the second ball was identical mass, so it's also 0.17 kilograms. Then it tells us, right, that the, which one do we want to have moving first? Anybody? Two moving first, okay. So that means that the initial velocity of ball 1 would be equal to 0 because it says that it is a stationary billiard ball, right? Then, moving at 4 meters per second, that means the initial velocity of ball 2, 4.0 meters per second. There's a couple other things in there with the angles, but those will come in a little bit later on. Good so far? At this point, we good? Okay. Let's draw ourselves at least a picture to begin with. Okay? Allie, you said you wanted 2 to be the moving one. Okay, so let's do this. That's not really the best. It's not really a circle. Let's go here. Is that better? Circle. No, that's not good. There. Yes. Okay. All right. Get rid of this. Get rid of this. And let's go here. Okay. All right, so that'll be ball 2, right? Then, and this will be ball 1. Okay. So it tells us that ball 2 moving at 4 meters per second, ball 1 stationary. However, like we discussed before, is the velocity really important to us in this problem? We said in the collision, what's the conserved quantity? Momentum is the conserved quantity. So we need to make sure that we're looking at the total initial momentum and the total final momentum. That's going to hold true even in this case, just like it did before. Okay? Actually, I'm going to do this. And let me cut this and go here. So this is where it all stems from. But, like we discussed yesterday, when we move this into 2 dimensions, we have to look at 2 conditions. We have to have momentum conserved along the x-axis, and then we also have to have momentum conserved along the y-axis. Are we good there? All right. So here's our initial condition. Right? If we were going to calculate the initial momentum of ball 2, what do we have to do? Mass of ball 2 times ball 2's initial velocity. We know the mass. I believe we know the initial velocity of ball 2 if I'm not mistaken, right? So we should be able to calculate what this initial momentum is. So why don't you do that right now? It does, but it's it's kilograms times meters over seconds. Let's just keep it as a number for now. All right. Then the initial velocity of ball 1, we take the mass of ball 1 times the initial velocity of ball 1, but it told us that ball 1 was doing what before the collision? It said it was stationary, so we got a big 0 there. Good so far? Okay. If, let's take this, I'm going to take this page and open this page. So let's get rid of this. Okay. It tells us in the problem that after the collision, the stationary ball moves off at 30 degrees to the right of the original direction, whereas the ball that was moving moves off at 60 degrees to the left of the original direction. So let's go here, okay, like that. Even though if you're watching the recording, you can't really see it, but, right? Here, if we take this, oh, sorry. Nope. There. There. So Billy, like you said, this one's going like this, right? And then this one is going like that. Off of the original direction. Okay, so if that's going to be that, if we wanted to, let's do this. Okay, so let's say this was our original direction. Okay. Okay. Then we could say blue's moving here, and it told us that that was 60, and then red is moving here, and it told us that that was 30. Okay. All right. Good so far? So here's our final condition. Yesterday, this is what we did. If we take a look at blue and red, right, are they on the x-axis of this problem? They're not. Are they on the y-axis of this problem? They are not. So we said yesterday, right, that we'd go components here, right, and then components here and components here. Okay? Okay?
Are they actually be on the X or Y?
Maybe. I can think of one problem where that does come into play. All right. I realize they're not straight, but that's okay because they're not steady. The problem with this is what? Do we know anything about this blue arrow and this red arrow? Remember, our initial problem is we're trying to find the final velocity of both of them. These are momentums, right, or momenta, but without a final velocity, we can't calculate a momentum, right? So that's kind of shoots our plan that we were working with yesterday down. We can't do it that way. All right, so this is how this problem becomes a little bit different. Just 0.68, is that what that was? All right, so there's 0.68. This was our total initial momentum, yes? So that means that when we're all said and done, that total initial momentum, or sorry, the total final momentum has to equal 0.68. And more important, where is this total initial momentum? It's on the x-axis, it's on horizontal, okay? So here's where this problem becomes a little different and convenient to how we had it, or convenient in the way that they explained it. All right, so let me get rid of this, because we said finding these components is pretty tough because we don't have enough to calculate the hypotenuse. Come on. Okay. However, it did make our lives a little bit easier, because if we go here, right, what do we see about these two angles put together? It makes a 90-degree angle, and that's important for us. Okay? So we know that this is 90 degrees. Okay? Now, watch me maneuver a little bit. Okay? Just watch what I'm going to do, and then see how, hopefully it'll make sense to you, okay? All right, I'm going to adjust just a little bit. Okay. I'm going to take this, and I'm going to move it here, okay? Except I'm going to adjust it just a little bit more. And move it there. Okay. Everyone see what I did with red? Okay. I moved it just parallel to where it originally was. Okay. Which means this is now 90 degrees as well. Does everyone see that? If you don't, raise your hand. Okay. So now we've got these two vectors, right? 90-degree angle between them. What does the resultant vector of those two look like? How would we draw it? The resultant vector we draw from the beginning of the first one to the end of the last one. Does that make sense? That's my resultant vector. Are we good with that term? We've talked about it before. Okay. Where does my resultant vector lie in this problem? On the x-axis. And if that resultant vector, which in this case is what did we say was conserved in this problem? Momentum. If this resultant vector lies along the x-axis, how big does it have to be? It has to be 0.68. Does that make sense? So here, let me get rid of this. So this is still 60 degrees. This has to be 0.68, but this is the momentum, right? Because this was the initial momentum. Good there? If I do some trig, if this is a 90-degree angle here, and this is a 60-degree angle here, what does this one have to be? That one has to be 30. What do we have now? What kind of a triangle, Billy? Well, kind of. More specifically, it's a, or I guess more generally, Billy, it would be a right triangle, right? And what do we know about that right triangle? The hypotenuse and a bunch of angles inside of it. Can we figure out the two sides? What did we say that those two sides are going to be for us? This is going to be the final momentum of ball 2. This is going to be the final momentum of ball 1. Does everyone see where I got that from? Can I at least get like a head shake, maybe? Yeah. All right. Do your math thing. Figure out those final momentums. Or momenta. Excuse me. All you lads there. Anybody? What is it? All right. Are we good with this value and this value? Even though I didn't draw them to scale.
Thanks to this stuff.
This is all math. Actually, this is actually physics and math coming together. Okay? Because, Frank, let me intervene at this point. Okay? The only reason this problem works this way is because why? what was the important part that they gave us at the beginning? What do we know about the red and the blue arrows? They're perpendicular to one another. Okay? And what you find out is that in these two-dimensional collisions, where you have this thing coming in or when you have this initial momentum coming in horizontally, running into these two things and splitting apart, this angle ends up being 90 degrees between the two of them. It's not math, it's just the way that it happens, Spring, and we make the math fit it, or the math fits it. It all just sort of fits together in a weird sort of way.
All right.
It's very kind of like appropriate for like a February 29th kind of thing. All right. Are these two circled numbers the answers to this problem? No. What did they originally ask us for? Velocities. But these are momentum, right? But hopefully we can get from momentum to velocity without too much trouble, right? What are we just going to do with these two numbers? Divide them by 0.17. So good. And then what's this one you're asking? What's it? All right, are we good there? The one we did yesterday, I had one of the final velocities, right? So we could break the red and the blue up into their components and solve this way. This one, I didn't have either of the final velocities, so we had to do it this way, but that was facilitated by the fact that we have this 90-degree angle between these two. Questions? Okay. So here, right, so going back to this, okay? Here,
And what happened?
this was 0.62 or something like that, right? That what it was, 0.62. And that meant 0.68. And that meant that on the x-axis, we again had to have 0.68, and that was what I used as the purple arrow. On the y-axis, there really wasn't anything to begin with, so we ended up with 0 on the y-axis.
Yeah,